Oscar. So he's from University of Valencia, Spain. So, and his title of talk is lasing in thin-based perovskites. I'm so sorry for the pronunciation. Thank you.
Okay. Just share the presentation.
Okay, thank you very much. Then this is a highly technical presentation, but okay, I will try to use it. Okay, this is a work. I have summarized several work developed in my lab together with other institutions in Spain, like Castellón, University of Castellón, University of Barcelona, and also a company in Poland that is producing solar modules or by injecting in flexible substrate, because this the perovskites are semiconductors. Perovskite, but is because of the structure of these components that are typically known as metal halide perovskites. Then this is a big group that is one is able to produce into thin films by solution processing techniques, as I will show you later. Very easy and very low cost and low CO2 fingerprint, because it's using low temperatures. And then this is the reason why it has been very popular in this. Is not working.
The laser won't work.
Maybe the battery. It could be worse. Okay, I'm sorry. I was thinking that the red was okay. Perfect. Then okay, we give you some more introduction than results, maybe. Firstly, okay, I will present some my group is mainly working in photonics related to optical properties, exciton recombination dynamics by photoluminescence, types of photoluminescence, and micro photoluminescence, and also with application for quantum technologies. Here there are several works experienced with our most powerful technique, that is a confocal microscope for doing micro PL spectroscopies at low temperature, from 4 Kelvin to temperature. For example, here is an application also to two-dimensional perovskites that we are able to study the fine structure of the ground state of this exciton transition. Also, with some other perovskites, like nanocrystal, for example, we can study with the same technique the emission of single nanocrystal that is reflected by these very narrow lines that, of course, more or less sweep the complete range of emission when you measure millions of these nanocrystal, of course. And this, however, if you go to room temperature, the homogeneous line width is practically as large as the inhomogeneous one. Then you measure many. And this is the reason why perovskite nanocrystal emitting in the green are being used, for example, for LEDs and feature displays of course, if one forget that is containing lead, this perovskite, but potential solution. Also some photonics, and in this case it's like metamaterials in this case, but for creating the case of this hyperbolic metamaterial that one is able, is practically like a micro cavity in the sense that we can have a partial effect in order to reduce strongly the spontaneous emission rate. And okay, why the successful history of this perovskite, metal alloy perovskite, particularly the story begins at the time more than 10 years ago, 2009, with the appearance of this within the family of the perovskites. In this case, the metal halide is given by a monovalent cation that can be organic, like ammonium, or inorganic, like cesium, rubidium, for example. And the most important, of course, the monovalent halide, iodide, bromide, and so on. Well, typically chloride, bromide, and iodide, no more. And the divalent metal, that is the important, of course, with lead, was the case of the popular increase of the efficiency of solar cells, more than 26%, with the use of methylammonium. Well, in fact, it's a combination of three cations, methylammonium, formamidinium, and cesium, typically with iodide in this case. Why the success in creating high efficiency solar cells with this method is because the strong absorption edge that very just here is highly sharp, the absorption tail, and that is very this kind of low energy tail and high absorption coefficient and low diffusion length that rivalize or is better, even practically better than crystalline monocrystalline semiconductor. But in this case is a very simple method to produce polycrystalline thin films. This is why the success of this technology. Okay, also not only absorption, but it's also exhibiting high efficiency emission or high quantum yield, no? Emission quantum yield, and then one is able also to produce active photonics, for example, amplification of light, like we have demonstrated in our lab 7 years ago. Even we have developed and integrated with a concept of the optical amplifier and a detector, and also lasers. Okay. I recommend, for example, this the most recent review in the field, natural material, where you can find two laser samples producing lasers using as cavities the crystal itself. In this case, are microdiscs, where the method for the amplification for the cavity is the whispering gallery modes, or nanocavities, where in this case the material is nanowires. Okay. In both cases, you can have very low threshold for the lasing effect. So here, for less than 1 microjoule per square centimeter, more or less similar to the case of microdiscs. This is also you can find here in my recently. They are also well, most of the devices that you can buy in the market, in the science market, of course, regarding the perovskites. However, there are a high issue that is the use because the material contains lead. Then, of course, for this reason, we launched 4 years ago a European project called DROPIT for investigating lead-free perovskites and with proof of concept of devices, of course, particularly the laser that I will present to you in this my talk. For example, this is from other authors, but it's a kind of sample where you can find lasing at several wavelengths depending on this is another kind of perovskite. It is not longer XB, X3, it's no longer a perovskite, but a two-dimensional, this is called Randles over two-dimensional basis of the perovskite that now you can have with respect to the three-dimensional lattice, you have confinement, and then if you go toward the two-dimensional case, you go to the visible 600 nanometers. So here, this is the phase purely two-dimensional, where the thin iodide cage is totally selected. Here there are two lead iodide cages, 3 and 4. Particularly, this material was synthesized as microplates. In this case, the lasing, the cavity is followed by the whispering gathering modes of the little light. And then also, this case was with a relatively low threshold. And the particularity is that room temperature was not measured, only is working at 80 Kelvin, this case, of this low temperature. Okay, then let's go into my results, my sources. The preparation of how we prepare this, in this case, is a three-dimensional, the three-dimensional perovskite for laminar iodide. Of course, in this case, the most important is to avoid oxidation because it's highly unstable, the T2 into T4. This is forming, if the quantity is not too high, is producing vacancy formation, and this is producing P doping or P character for this material. No? However, if we add tin fluoride, we in this case we reduce enormously the vacancy because we go back into the tin2 oxidation balance, and then we reduce the P dop, like shown here, no? By the reduction of the absorption each from 1.4 to 1.2. And this also, of course, increases the optical quality, the optical quality and electronic quality for emission purposes, for light emission purposes. That is our main focus, of course. The method of preparation is depicted here. Was published as an application for solar cells the last year, and we demonstrated the high operational stability. And it's very simple because it's preparing the formamidinating perovskite with the additive of tin fluoride. And we also add some other additives in order to also to refresh the iodide concentration in surface, or the iodine chemistry on the surface, in order to gain also in stability. Finally, there are, other than the chemical additives, the whole thin film is improved by light soaking nitrogen during several days. These solar cells are shown here. We are right to have practically, well, not record, but very high, 11% of solar efficiency, and the important work study with respect to the case of vanadium iodide without the atoms. Also recently, we evidenced the origin of this stability or the instability. At the end, of course, the material turns into the appearance of thin oxide formation from the surface, and then this is the origin of the final composition of the material after many days. Well, in this case, with the improved formulation, we can, of course, improve the exciton lifetime in emission that is observed, as you see here, so for around 880 nanometer, or more than 900 at the low temperature. And the most important is the inhomogeneity, because it's just the origin of the observation of random lacing that I will be explaining later. But this is the most important. Sorry. Because although we have studied from low temperature to room temperature the observation of amplification of the continuous emission when we enter into the regime of stimulated emission, and the appearance of random lacing. And it's the only case where the thin perovskite is winning the lead perovskite. Random lacing can be used for several applications, like spectral-free imaging, sensing, and biomedical information security. Of course, I have not developed those applications, but it's the general field of application for the random lacing. Okay, in this goal, we have used two kind of incident light area. It's a large excitation spot and, let's say, short excitation spot, in order to study better the random lacing effect, or to demonstrate that we have a random lacing effect, because the amplification of the continuous emission is proportional to the exponential of the light length of the cavity associated to the cavity that is formed by a scattering of light in different range of the polydistant. And then in the case of large excitation spot, the threshold for amplification of the continuous emissions and random lacing should be smaller than in this case. The number that I think are most of the best measured in this material is around 2 microjoules per centimeter, the threshold that is shown here. See the threshold from this is a linear variation, and then here appear the stimulated emission, and then we enter into the regime of amplification of the photonic emission. The threshold is very low. Under faster excitation, we are using 355 or 532 nanometer. And increases to 4-5 microjoules in sample without the treatments and the additive that we are using. That we were using for the production of films. And increases 1 order of magnitude approximately what will go into room temperature. But for that room temperature is also possible to obtain that is telling us that the quality of the material of the films is very high. Then this is the went down to the results of regarding random lacing that I will summarize here. Steve, but mainly is that as I told you before, the random lacing is due to scattering at non-crystalline grains, defining a certain long cavity in the material. Long cavity length that is the order of 100 microns typically or more. And then we observe, as you see here, very narrow lines. These narrow lines are the random lacing effect. The narrow lines of the order of 1.1 nanometer. The most important characteristic of this random lacing in our material, in the thin perovskite films, is that these modes are reproducible with power, with time. All the peaks are there. The low beta parameter, this is due to the equation of the laser, is very low because it's very long circuits for the light. The forming the cavity for amplification, and it's characteristic of the random lacing, of course. And this is in comparison to lead perovskite, where practically no random lacing is observed. And the reason for the observation of this spectrally unusual, spectrally reproducible, high Q factor random lacing is we attribute to the inhomogeneously broadened emission line that in fact we can have several lacing circuits, but spectrally they don't enter because they are separated in energy. Okay. And then this is the reason why we can observe spectrally reproducible. Okay, we have also made some application. This is not typically doesn't produce a laser, but is used for amplification of light, for example, in photonic devices. But in this case, we will observe also random lacing. I will describe briefly. This is the device consists of a silicon dioxide, typically 2 micron, in order to confine the emitted light. In this case, as mentioned before, around 900 nanometer. It's practically a monomode waveguide because coupled with a PMA of around 1 micron on top. Okay, you can have more information in our previous works. Using, in this case, using LED, of course, light, but for the physics, I don't know. These are the equation for the amplifier. The production of the stimulated emission is giving us amplification. And I mentioned, okay, we are using it, and it's not visually as visual as in previous cases, but we also have random basing, or random service regime that is linear, beyond linear, or let's say superlinear behavior of the intensity of the emission, and later again the random basing regime also link. And with this device, of course, due to the high confinement for the light in the vertical direction, we can have very low threshold of around 0.1 microjoule. That is also important for devices, of course, for having highly sensitive devices. But we have also demonstrated in flexible substrate. In this case, it's a plastic, it's a PET substrate, where we deposited the non-luminescent iodide film and cover it also with film. The amplification is also observed, and also the random lacing, as shown here, even if the threshold is a bit higher, because of course the quality is not so good as in the case of a silicon dioxide very flat substrate. But in this case, in this kind of planar waveguide, we have also a directional emission due to the very low thickness of the active film, especially when we go into the lasers again, that can be also useful for some polarized sensitivity application with polarization sensitive experiments characteristics. And the fact that we are using the flexible substrate, we can also tune a bit the wavelength of operation, shown here. Of course, the threshold is the issue is that we also mechanically we are deforming the film, and then also the threshold is damaged. And okay, finally, to finish my talk, we have also working now with cavities in order to get real monomode lacing devices. In this case, is a microcavity